Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you for the invitation. Yuri and I got connected by kind of an online math conversation about 3 or 4 months ago or so. And that's how I learned of the work, and I know with co-authors as well. And so he invited me to come down and give a talk about some of the number theory that goes into the real work. So I'm happy to do that. This is, I guess it's fair to say, this is going to be an expository talk. There's a lot of pretty mathematics in here that's, I think, is just kind of fun for its own sake. And so I think those of you who haven't seen these sort of number theory results before, hopefully you'll just get to see some cool results. Those of you who have seen the results before, maybe I'll be able to say some interesting things about how that they're actually proved, at least give some idea of the tools that go into it. I certainly, well, I guess pointing to the outline here, we're going to be looking at just the numbers that can be written as the sum of 2 squares or 3 squares or 4 squares. It's a reasonably interesting problem for any number s, but these are the classical s's. S equals 1 is a little bit interesting, but I think you can figure it out. So first, we'll just talk about characterizing which numbers. If I give you a number, how can you tell yes or no? Can it be written as a sum of 2 squares, for example? And then we can go on to actually count how many such numbers there are. Okay, we'll talk about what that means in a second. There are infinitely many, of course, but we can still sort of say how thick on the ground they are. And then if I can be written as a sum of 2 squares, for example, maybe there's more than one way to do it. In fact, there almost always is more than one way to do it. Say a little bit about how many ways there is to do that. And then I do have a fourth point on the outline, which I almost certainly won't get to in the talk, which is really talking about the application of this to the research here at Microsoft. I should say that I want to make the talk nice and finite, and of course I definitely welcome questions at any time. But I have nothing else to do this afternoon. I'm happy to sit around afterwards and talk about any of this stuff as long as you guys want to talk about it. So you can ask questions during. If we don't get to number 4, that's fine. I'll have plenty to say about it afterwards when people who are really interested can stick around. So your schedule is what I want to abide by. So let's start with the first one, just characterizing which numbers can be the sum of s squares. All right, so let's just start when s equals 2. When is a number equal to the sum of 2 squares? And in keeping with the high technology level of my medium, I will use a high technology notation. When is n the sum of 2 squares? So if you look at the data, the set of numbers that can be, I'll write in red and write in black, and the ones that can't, I'll write in red. So 1 and 2 can be, 3 can't, maybe I'll just use both hands. 4 and 5 can, 6, 7 cannot, 8, 9, 10 is good, 11 is bad, 12 is bad, 13 is bad. Are all these bad? I feel like one of these is messed up, so. I am, 13 seems pretty good, huh? So let's put it here. And then 16, and this is as far as I'll go. And this is the kind of thing that if you're a 17th century mathematician, you look at this list, and it's actually kind of a fun game to, well, you make it longer. It's a fun game to figure out the pattern. And of course, I will instantly spoil that fun game for you because I'm going to tell you the answer. But it can be done. It's not trivial. One of the ways that we can sort of look at these omissions is notice that multiples of 3 are on this list. Not 3 times 3, right? 3 times 3 really can be written as a sum of 2 squares. It's 3 squared plus 0 squared. We also have a couple of multiples of 7 on this list. We have a multiple of 11 on this list themselves. And 3, 7, 11 have the property that they're the first numbers that are congruent to 3 modulo 4. And it turns out that it's not too hard to show that this is a restriction that lasts. It's going to produce lots and lots of red numbers. So in the spirit of trying to have one complete proof in every math talk, let's get it out of the way right away. We'll even call it a lemma. Let's suppose that n can be written as the sum of 2 squares. And let's suppose we have a prime, p, that's congruent to 3 mod 4. It's 1 less than a multiple of 4. Anytime I write p, it'll be a prime in this talk. And it happens to divide n. Then, in fact, its square has to divide n. So for example, if we have a number that is a sum of two squares, but it's a multiple of 3, it really has to be a multiple of 9. That's what this lemma is going to say. And this actually explains all of the red numbers that we've written so far. All right. So why is this true? Well, we have, let's say, p divides n, which can be written as the sum of two squares. It's a squared plus b squared, like this. And if we write this as a congruence, this says that a squared plus b squared is congruent to 0 mod p. It's just a multiple of p, saying the same thing. Or we can move the b squared to the other side of the congruence, that a squared is congruent to negative b squared modulo p. Now let's suppose for a moment that b itself is not a multiple of p. Suppose it's not. So suppose p does not divide b. That means that it has a well-defined inverse. We can act like it has a reciprocal mod p. And we can actually move it to the other side. B inverse A, all squared, is congruent to negative 1 mod p. And it's actually well known and not too hard to show that there is no number whose square is congruent to negative 1 mod p if p happens to be a prime that's 3 mod 4. Kind of a classical, one of the first things we might learn if we're studying quadratic reciprocity or something like that. So, but x squared congruent to negative 1 mod p never has a solution if p is a prime that's congruent to 3 mod 4. So this supposition has to be wrong, that p actually has to divide b. So p has to divide b, and then there's a whole cascade of things that p has to divide. P will divide the difference of two multiples of itself, and that's a squared. And so that means p has to divide a itself because it's a prime. And now if p divides both a and b, then p squared divides a squared plus b squared. So the statement of the lemma is sort of like a global version of this nice local fact that x squared congruent to minus 1 mod p doesn't have any solutions. And if you just do a pretty simple modification of this, then you can do sort of any odd power of p. So this is a statement of the lemma, but similarly, you can get a whole sequence of lemmas that says if p cubed divides n, then p to the 4th divides n, and so on. You can't just be sitting on an odd power of p. They have to pair up. It's reminding me of the talk that I just went to, but not the same kind of pairing. Okay. So this gives a whole bunch of obstacles for being a sum of two squares. This generates a whole list of red numbers, in fact, a whole bunch of red numbers. And the cool thing is that this is the only obstacle. The only obstacle to being a sum of two squares is having a 3 mod 4 prime in your factorization to an odd power. So we'll state this as a theorem. And this is, I think, from a mathematical point of view, one of the reasons why this is such a nice subject is that the problem is about addition, but the answer is about multiplication. It's about the factorization of the number. So this is really cool to me. I don't know. So I guess this was a proof was first written down by Euler in the mid-18th century. Certainly a proof was claimed by Fermat, but Fermat almost never wrote down proofs of anything. He just taunted his frenemies with them. And it might have even been noticed earlier. So let's factor the number n as into its prime power factorization. So p1 to the k1 up to pr to the kr times q1 to the L1 up to QS to the LS. And the P's will be 3 mod 4, and the Q's will be primes that are not 3 mod 4. So primes, so PI are primes congruent to 3 mod 4. Most of them are probably 1 mod 4, but I hope you'll give me one exception. Of course, as number theorists like to say, most primes are odd, but 2 is the oddest prime of all, so we tend to avoid it where we can. So the QI are primes not congruent to 3 mod 4. Then the theorem is that this is the only obstacle. N is the sum of two squares, if and only if each ki is even, so that we avoid this obstacle here that you can't have the odd one. And that's all you need. That's the only thing that you need. And I won't give the entire proof of this, but I will boil it down to the important statement that needs to be proved. So this is, I guess, a sketch or a couple of ideas that are still cool. And proving this theorem comes down to a particular magic identity. And it's just some polynomial identity that you can verify for yourselves if you want. If you take the product of two sums of two squares, again, mixing multiplication and addition in what seems like a dangerous way, this turns out to also be a sum of two squares. In fact, it's AC minus BD all squared plus AD plus BC all squared. And it's just something that computers do better than us. So this magic identity says that if I'm a product of a bunch of numbers that are sums of two squares, and I myself has to be a sum of two squares. Of course, you can iterate this. You can make as many factors as you want. So what building blocks do we have to show are sums of two squares? So the theorem follows from, well, some of our building blocks are things of the form p squared, when p is 3 mod 4. But those are clearly the sums of two squares. It's just p squared plus 0 squared. And then there's the one even prime. Yes, I think we can figure out that's the sum of two squares. And then the last building block that we have is that if we have a prime q that's congruent to 1 mod 4, then q can always be written as the sum of two squares. And this is not a trivial statement, but it's not super hard either. It would be something that could be taught in an undergraduate number theory class. Take a lecture or so. So this is the crux of the proof. As long as we can show that every 1 mod 4 prime can be written as the sum of two squares, then we can assemble all the pieces together to get all these black integers here. Right. So anything else to say about sums of two squares? I think that's, yeah, please.
Do you regard the top identity as accidental?
No, I was going to say this.
Complex number.
Exactly, that's exactly what it is. So this is, get to switch around the order of the talk, this is exactly right. So note that this identity can be rewritten as the multiplicativity of the norm of a complex number. So if I write, instead of a squared plus b squared, if I write the norm of the complex number a plus bi, then if we multiply that by the norm of the complex number c plus di, then what we get is the norm of their product, a plus bi, c plus di. And now if you multiply this out, in fact, I don't remember this identity, I remember this identity, and then I just pretend that I'm doing something cool. The real part of this is AC minus BD, and the imaginary part is AD plus BC times I. So that's exactly right. This is not an accident. Well, I don't know, it's the same accident as this. There's complex numbers are behind the scenes here.
Eulerian accidents.
Yeah, I guess. There are no Eulerian accidents, is that the theme? And the fact that this has something to do with the complex numbers might explain why the next thing I'm going to talk about is not s equals 3, but s equals 4. Because when s equals 4, we have kind of an analog of the complex numbers, namely the quaternions. So it's actually a little bit prettier to talk about s equals 4 than it is to talk about s equals 3. So let's do that very thing. Unless there are other questions so far about sums of two squares? Oh, yeah. Absolutely, yeah. And depending on exactly what you insist upon of your algebraic structure, I think they're called division algebras or something like that, then it's been proved that they only exist in dimensions 1, 2, and 4. So you have the real numbers, the complex numbers, and the quaternions. And there's nothing as nice in any other dimension. I think there's something in dimension 8, but it's not associative or something like that. Anyway. Yeah, it's a little nasty. Yeah, that's right, yeah. But useful. Ooh, that's a controversial claim. Like much of math, I know of no use, but I won't dispute that it's actually useful. Okay, sums of Foursquares. All right. So I think the right thing is a division algebra. It's what do you want? So if you're going to go to dimension 4, you've given up commutativity, but I think you still want like both-sided cancellation or something like that, right? So it's
I just need the hook so I can go.
Fair enough. Yeah, division algebra should be close enough to get the right answer. Yeah. Okay, sums of Foursquares. So when is n equal to the sum of 4 squares in our lovely notation? And if you start doing the data for this one, then I'm very, very sure that you'll be able to find the pattern, because there are no red numbers. If you just keep looking, you'll find that everything you can write down works fine. And this is actually a theorem. So Lagrange's Foursquare Theorem, later 18th century, and all of them. Every positive integer can be written as a sum of 4 squares. So this is really nice. You might have guessed, because we talked about the quaternions here, that there should be maybe some magic identity, a dimension 4 magic identity. And there is, and I won't write it down, but you and I could figure it out at the same speed, because we would just write down the quaternions and try to remember how to multiply them. So the sketch of the proof is the same. You use the surprising multiplicative structure of the problem to reduce it to building blocks. So we write down, which I won't do, but we write down the magic identity corresponding to, I guess, the quaternion. So the norm of A plus BI plus CJ plus DK times, I don't even know what, am I going to get to the right letters here? E plus FI plus, ooh, that was a close call. So you just write out these norms, and you write out the product, and you write out the norm of the product. OK, so there's some magic identity, some 8-variable polynomial identity, which is even cooler than that. And what that shows is that as long as you can represent every prime as the sum of 4 squares, then you can assemble it together and represent every such integer. And note, by the way, this is totally constructive. If you have an algorithm that does the prime case, then this tells you at least one such representation. We'll get to later to the issue of trying to find them all. So now the crux is just to show that every prime can be written as a sum of 4 squares. And again, this is not trivial, but it's also not super hard. Let's see. This one, I was trying to figure out, in all of this stuff, there's attributions of who first wrote down a proof, or maybe who first wrote down a proof that today we call a correct proof. But then there's the first person who actually noticed it and whatever. So I think someone before Fermat noticed this. In fact, I thought I wrote it down. No, I just said it earlier. Girard or something. Some people say that this was actually in Diophantus's 3rd century book, that every integer can be written as a sum of 4 squares. So at least as an assertion. Yeah. So and now if we go back to 3 squares, by the way, of course, once you can be written as a sum of 4 squares, trivially you can be written as a sum of 5 squares or 6 squares or whatever, if you're going to allow 0 or whatever. If you don't want to allow 0, there's still some interesting things to say. But going back to 3 squares, one is n the sum of 3 squares. And this turns out to be a less pretty answer. The characterization is kind of pretty, but it's definitely a different problem because there isn't any such multiplicative structure. And I don't just mean that we haven't figured one out yet. I can easily write down 2 numbers of this form whose product is not of this form. In fact, you could easily do it too if I stop talking and let you think. But I won't do that. So 3 is the sum of 3 squares, 1 squared plus 1 squared plus 1 squared. 5 is the sum of 3 squares, 2 squared plus 1 squared plus 0 squared. But 15, their product is not the sum of 3 squares. And in fact, it's not hard to show that 15 is not the sum of 3 squares, but in fact, you can actually show it just by looking mod 8. The only squares modulo 8 are 0, 1, and 4. And try as you might, you're not going to add 3 of those together and get 7 mod 8. So in fact, no number that's congruent to 7 mod 8 can be written as the sum of 3 squares. You just look mod 8 at someone's supposed counterexample and prove them wrong. And that's almost the only obstacle. Being 7 mod 8 is almost the only obstacle. Just have to pretty it up a little bit. Powers of 2 get in the way. Yeah, please.
In the 2 square case, the only obstacle was 3 mod 4.
That's right.
In the 3 case, we're looking at 7 mod 8.
Yes.
I somehow missed in the 4 case there wasn't an obstacle.
Correct. That's absolutely, yeah, there's no obstacle whatsoever. Okay. Local or global obstacle, yeah. Everything is kind of beautiful. In fact, I didn't say anything about proving these cruxes, proving that every, say, prime that's 1 mod 4 can be written as a sum of 2 squares, or proving that every prime in the world can be written as a sum of 4 squares. There's several different ways of proving that, but one way of proving it is first showing it locally. In other words, showing that there always exists a sum of 4 squares that's a non-trivial one that's 0 mod p. And then, so that gives you a multiple of p, and then there's the classical way is there's sort of a descent argument that if you have some multiple, then you have a smaller one, you get all the way down to p itself. May or may not be the slickest proof we could come up with, but I think these are the first ones that, like Fermat loved descent arguments and so on. So these are really local obstructions, right? If I just look at the squares mod 4, there's 0 and 1. I can't get 3 mod 4. Right, case is closed there. Same thing with mod 8. But there are no local obstructions for 4 squares. It's enough to fill up all the possible residue classes. That doesn't, of course, automatically mean that there's no global obstruction, but it turns out that there's not. Okay, so what's the answer for 3 squares? So the theorem here, which I just looked at my notes and forgot, 1790 or so. Apparently people got really excited about this in the second half of the 18th century. Oh, there it is. Aha, all right. So this is one where it's often attributed to Lagrange in like 1898, or 1798, sorry, but then apparently the proof wasn't complete and Gauss came along and picked it up because he wasn't busy enough. Fermat, I think, also said he could do this, but he says a lot of things. So n can be written as the sum of 3 squares if and only if, it's not of a particular form. It's not a power of 4, 4 to the k, times a number that's 7 mod 8. So the 7 mod 8 is the obstruction we've seen, and then you can sort of factor out powers of 4 and reduce to the same obstruction somehow. So for example, 4 times 7, 28 cannot be written as the sum of 3 squares.
Did Fermat make any prediction which proved to be wrong?
I don't know of one. He made so many. I mean, it's hard to know. Of course, is wrong meaning like typo level wrong or like seriously wrong? I don't know of any offhand. Yeah. So, like for example, this is usually the 2 squares usually called Fermat's 2 squares theorem, even though I think he never published a proof. But he just had the assertiveness to pull it off. I guess I don't know.
So you're missing a knot.
I'm missing a knot.
There's a knot you can see.
Thank you. All right. So to only a mathematician, it's 100% wrong, pretty close. Yeah.
I just have one question. So that happened in 1749, and that can very easily be extended to this. So like 20 years of a time to do this.
Sorry, to the 4 squares one?
Yeah, it's not very easy. So the crux of this, that implies the crux of this quite easily.
That's
Because
the sum of it.
if it's a prime 1 mod 4, I can easily do it. And
Okay.
3 mod 4, 2 plus.
But this one only, this right away only works for primes.
Okay.
Yeah, yeah. There might be some sort of way to reduce it, I agree. Certainly the standard proofs that I've seen just sort of do it from scratch. Yeah, but there might be a way, And I guess you have to know about the quaternions, but, you know, people look at these things. So. Yeah. Okay, so I won't really say, in fact, I don't think I'm going to say anything about that proof. This is somehow a less elementary proof. The other two, like if you held me down and made me write out a proof, I could do it, but this one I couldn't. I'd have to look some stuff up. So. Let's see how we're doing for time. I guess I won't write anything, but I'll just say that as a detour, there's an interesting generalization of this where you change the power to a different power. So instead of looking at numbers that can be written as the sums of squares, you look at the sums of cubes, sums of fourth powers, and so on. And it turns out that as long as you allow yourself enough variables, you can always do it. So there are analogs of the Foursquare theorem for cubes. Like every number can be written as the sum of 9 cubes. Every number can be written as the sum of 19 fourth powers. And this is known as Waring's problem because a fellow named Waring wrote those assertions down and then he wrote and so on. And then he went and got a beer or something like that. So Waring's problem. Yeah. And there's definitely active research on this to this day. Like how many kth powers do you need to write every possible integer, every sufficiently large integer? So for example, for cubes, we know that you need 9 cubes in general. In fact, if you try it for the number 23, you need 9 cubes. It's just not many things to try. But you don't need 9 cubes very often. For all sufficiently large integers, you only need 7 cubes, for example. But we don't know the right answer to that question. If you discard finitely many examples, how many cubes do you need to write all sufficiently large integers? And we know it's between 4 and 7, but we don't know the answer, for example. So.
In all these cases, you have this multiplicative.
No, in very few of these cases. So the proof of this kind of Waring's problem stuff in general is by an extremely different method. The circle method would be the 2-word tag. It's quite a bit more complicated. Very interesting stuff, but it definitely for another time. But if you want to write every integer as a sum of, 100th powers, as long as you allow yourself enough of them, then you can do it. So I don't know why you'd want to, but that's okay. So I guess the next item in the outline was counting such numbers. And when we talk about, or when I talk about counting an infinite set, it's an infinite set of positive integers. What we're talking about is we're going to look at the number of integers up to x, such that n can be written as, well, I guess we'll start with 4 squares. That's the easiest one, as a function of x. Okay, this particular one is really easy because every integer can be written as a sum of 4 squares. So, so for 4 squares, 100% of integers can be written as a sum of 4 squares. For 3 squares, again, the proof is a little untidy, but the answer is quite tidy. And it's easy to work out the proportion of integers that are of this form is exactly 1/6. So for 3 squares, 83.3% of integers can be written as a sum of 3 squares. But now if we look at just 2 squares, then it's a little harder to figure out how many integers have this property. Right? So it's a less obvious property. Luckily, smart people were born before us. They've done this. So first of all, I'll give you a little bit of data. So this is going to be the number, so I guess the first column will be x, and the second column is the number of integers up to x that are the sum of 2 squares. So we'll count up to 10, 100, 1,000, and 10,000. 7 of the first 10 integers can be written as the sum of 2 squares, 43 of the first 100 integers, 330 of the first 1,000 integers, 2,749 the first 10,000 integers. Care to make wagers? No, of course you don't. But there's, what's that?
Close to 1,007.
Okay. So should the answer be x to the log 10, 7 over log 10? Maybe? I don't know. Okay, so this data could support almost any assertion, so that's why it's fun to bet on. But it turns out in the limit, the answer is 0%. So the condition that I just erased of having this multiplicative structure where you don't have any 3 mod 4 primes to an odd power turns out to exclude almost all the integers. In the limit, there's 0% of them that survive. But we can actually say something very much more precise than that. And this is a theorem of Landau from just over 100 years ago. If we look at the number of integers up to x, that can be written as a sum of 2 squares. And it's actually asymptotic to a smooth function. So this just means the limit of the quotient of these two functions tends to 1. If you plot them, this is some step function, this will be some smooth function. Zoom out far enough, they occupy the same pixels on the screen. That's all this means. And what is this function? It's a particular constant times x divided by the square root of natural log of x. And the constant k is pretty strange. It does betray the, it has clues about this multiplicative structure hidden inside it. It's 1 over the square root of 2 times a product of 1 minus p squared all to the minus half. And this product is over all primes that are congruent to 3 mod 4. So it's an infinite product. By the way, I should mention, I just tossed out casually, oh, it's an infinite product. It's not completely trivial that there are infinitely many primes that are congruent to 3 mod 4. I mean, there are infinitely many primes, and they're all congruent to either 1 or 3 mod 4. But we have to think a little bit to show that we actually get both types infinitely often. It's actually kind of an interesting observation that Chebyshev made in the mid-19th century, which I've done some research on this topic, where if you look at the two graphs of these counting functions, 3 mod 4 primes, 1 mod 4 primes, we know that asymptotically they each have 50%. So if you zoom out, they occupy the same pixels on your screen. But if you just look, the 3 mod 4 one always seems to be ahead. And he actually asked, oh, does that always happen or whatever? And this is sort of a prime number races or something like that. Is this
Some
thing.
funny kinship to both box conjecture in the fact that they're both there all the way.
A little bit, yeah, somewhat similar. Like, sort of a kind of a parity phenomenon, I guess. Anyway, but as I guess the soundbite thing I wanted to say is that 50% of primes are 1 mod 4 and 50% are 3 mod 4. And then there's one that's neither.
I think maybe they do overtake each other infinitely often.
They do. That was a famous theorem of Littlewood from the 1910s, and I think people by that time expected that it didn't happen. So when Littlewood proved that they do happen, the first point where there's more primes that are 1 mod 4 than there are 3 mod 4 is 26,861. And it's actually the first of a pair of twin primes. So 3 mod 4 says, oh no, you don't right away, and then starts leading again until past 600,000. So it's actually quite rare, and there's been some interesting research in the 1990s to try to quantify that rareness. So in some measure, the 3 mod 4 is ahead of, in this race, 99.59% of the time. So it's kind of cool. Anyway. The leader changes infinitely often. Yeah.
So the general thing is Dirichlet's theorem, but of these two, is like one of them is completely elementary, but the other is not. So the 1 mod 4 and 3 mod 4.
Yeah, I mean, because I'm going on your schedule, I don't really care if I finish what I have to say. This is it's an interesting thing. So what's the, let's do the proof. We'll put more, well, you get a bonus proof. Okay, so what's the usual proof what's Euclid's proof that there are infinitely many primes? Okay, you suppose that they're not. You suppose there's only finitely many primes. You multiply them all together and you add 1. You show that thing has to have a new prime factor. So I like to say with various degrees of success that you can also make this into a proof that there are infinitely many composite numbers. Suppose they're not, then just multiply them all together and don't add 1.
So that immediately yields that there are 3 mod 4, because if you make it 3 mod 4, you can absolutely.
So infinitely many primes that are 3 mod 4, it's exactly as you say. You just change this slightly. So if not, if we've written down all the primes in the world that are 3 mod 4, there's only finitely many, then you can look at this number 4 times their product plus 3. In fact, to be completely honest, let's have P1 equal 3, and let's not use P1 here, because I don't want this to be a multiple of 3. So this is a number that's 3 mod 4, and therefore it must have a prime factor that's 3 mod 4. In fact, it must have an odd number of such prime factors. But it's not divisible by any of the known 3 mod 4 primes. So this case is an easier case. To do something like this for infinitely many primes that are 1 mod 4, you have to be a little bit trickier. You can set up the number, so now P1 to PK are all 1 mod 4, and we're assuming that's all that there are. And you can do this if you set up the number 4 times P1 up to PK all squared plus 1. Because there's another little elementary factor, which is quite related to the one we had down here before, that any number of the form 4x squared plus 1, all of its prime factors have to be 1 mod 4. And it's essentially the same argument that negative 1 is not a square mod 3 mod 4 primes. So you do have a slightly less elementary, but still you can just write it down. And people look for, people would love to prove Dirichlet's theorem that any nice arithmetic progression has infinitely many primes with this way. But in fact, you can generalize this to a point, but sort of to 0% of the cases. So. Okay, did I want to say anything else about Landau's theorem? Well, I wanted to sketch the proof. That might be ambitious. Okay, let me not sketch the proof, but let me at least write down the object that comes up. So the soundbite version of how this is proved is that there's actually a function of a complex variable, a nice analytic function, or a sort of analytic function, that goes along with this problem of trying to characterize the numbers that are sums of 2 squares. And one can actually get a formula like this by taking that function and doing some contour integration. So it's definitely not a trivial way to proceed, but it can be done. Let me just write down the object that I'm alluding to. So this is, I guess, related to the proof of Landau's theorem. And the idea is to write down a nice series that has some arithmetic content to it. So before I do this one exactly, let me just write down the Riemann Zeta function, because it's kind of a slightly simpler version of what this is. So this is more for comparison than strictly related. But the Riemann Zeta function is certainly well known in mathematics. Zeta of z is just the sum of the negative zth powers of all the positive integers. So for example, there's the classical Euler formula that if you take z to be 2, the sum of the reciprocals of all the squares is exactly equal to pi over 6. In fact, Euler wrote about 500 papers, but this was one of the first. This is the one that vaulted him onto the international mathematics scene. It's figuring out this exact value. But in general, we can think of this maybe for any complex number z if we want. And one way we can see this is connected to the primes is that we can actually factor this into a so-called Euler product. So this is a product over all primes p of the following term. It's 1 plus p to the minus z plus p squared to the minus z plus p cubed to the minus z, and so on. Each factor is an infinite sum. And the way we can see this is, well, every number n decomposes into a factorization of a product of a bunch of primes. And so if it's p squared times p times p times p cubed for different p, you just sort of select it like an a la carte menu from this product. So if you just do the FOIL, if you distribute this infinite product of these infinite sums, you'll pick up all these integers. This actually is a nice geometric series, so the way that this is usually written is a product over p, 1 minus p to the minus z inverse. So this is, I guess, in a nutshell, why the Riemann zeta function has anything to do with primes. And if you've ever seen this before, obviously its properties as an analytic function are crucial for understanding the distribution of primes. The reason I write it down here is because there's a function, if we take the same function but only sum over the integers we care about, only the sums of two squares, then we get a related function that also has a factorization because this is a multiplicative problem secretly. So if we look at, I guess just call it t of z, t for two squares, and let's define this to be the sum of n to the minus z, where n is equal to the sum of two squares. And I guess let's not try to do this with 0. Then we can do this same factorization, this a la carte method. If p is a prime that's congruent to 3 mod 4, then it has to occur to an even power. So we get 1 plus p squared to the minus z plus p to the 4th to the minus z, and so on. So this term is slightly different. We only get the even powers of p. But for the other terms, we get exactly what the Riemann zeta function had. So let's say q not congruent to 3 mod 4. This does include q equals 2. 1 plus p to the minus z plus p to the minus 2z, so on. And so if we do this as a geometric series, this is the product over p congruent to 3 mod 4, 1 minus p to the minus 2z inverse. And then the rest looks like the Riemann zeta function. The product, q congruent to 3 mod 4, 1 minus p to the minus z inverse. So I would certainly, if people later on want to ask me more details about the proof, I can go on to what's going on. But the interesting thing here is that this includes about half the prime. So this looks kind of like half the Riemann zeta function in some sense. And in fact, this function here is the square root of the Riemann zeta function times a nicer function. So the good news is we can use our knowledge of the zeta function to sort of examine this. The bad news is that square root, when you're talking about analytic functions, is really nasty. You don't just have an isolated singularity anymore. You have to do a branch cut or something. So, okay, so anyway, lots of interesting things to say about that. Leave it for another time. Let's move on to the final bullet point that I had any expectation of getting to, counting the number of representations. So if a number can be written as a sum of two squares or 3 or 4 squares, then how many ways can it be so written? And it turns out you and I, if we're like, okay, how do you write 5 as a sum of two squares? And you're like, there's one way to do it, 2 squared plus 1 squared, okay. But it turns out that math prefers to be really pedantic and say, no, there's actually 8 ways to do it. You can put plus or minus 2, you can put plus or minus 1, you can put them in either order. So the formulas work out nicer if you include all of the redundancy. Did I just lose? Here it is. Okay. So let's let R sub s of n be this counting function. It's the number of ordered s tuples, I guess, a1 up to as. And these can be positive, negative, or 0. And they're ordered such that the sum of their squares is equal to n. Of course, we'll be worried about. This is actually an interesting question even for larger s, because the number certainly changes. And starting with s equals 2 first, I want to say something a little bit about the average behavior of this function. It's actually easier to work out than the individual behavior. So let's imagine we're looking at R2 of n, the number of ways n can be written as a sum of two squares. But now we're going to sum this over all n up to some cutoff point x. All right, well, just by the definition, we sum over n up to x. And this is just the number of ordered pairs AB such that a squared plus b squared is equal to n. But now the n doesn't really matter anymore. It's just a squared plus b squared should be less than or equal to x is the only restriction. So this is just the number of ordered pairs, lattice points, points with integer coordinates in the plane, such that a squared plus b squared is less than or equal to x. Yeah, this is the number of lattice points in a big disk. And as long as you have a shape that's not really ugly, then the number of lattice points is basically the area. So this is asymptotic to the area of this disk of radius square root of x. So area of a disk of radius square root of x, and that's just pi times x. Well, I guess this one's an equality, pi times x. And one interesting thing to note, remember that most of these R2 of n's are equal to 0. Right? 0% of integers actually have a representation at all. So we have a reasonably thin set of integers. Counting function looks like x over the square root of log x. But the total number of representations is like x. So if I have a representation, I actually have a lot on average. I have something like the square root of natural log of x on average. So if R2 of n is greater than 0, then, let me not put parentheses, this is sort of a lie, but on average, R2 of n sort of has size square root of log x. But this definitely is an average statement. The function R2 fluctuates quite a bit. There's let me write down. There's a multiplicative formula. Okay, I guess what I'm trying to say is that the formula for the number of representations depends on the factorization. The more composite n is, the more representations you have. And so it's like a divisor function. It really fluctuates quite a bit. So there's lots of ways to write this formula down. Two equivalent ways are as follows. So R2 of n is equal to 4 times the number of special divisors of n. So d dividing n. And d is special that it only has good primes in it. So every prime p dividing d satisfies that it's congruent to 1 mod 4. So if you listed the divisors of n, throw out the ones that have a 3 mod 4 prime factor, in fact, throw out the even ones as well, and then just count the ones that remain. That's the same up to this factor of 4 as the number of representations. Another way one sees this written sometimes is that this is the number of divisors of n that are 1 mod 4, just the divisor itself now, minus the number of 3 mod 4 divisors of n. And it's fun if n hits one of these obstacles, if it's divisible by a 3 mod 4 prime to an odd power, it's fun for you to work out by hand that this is actually equal to 0, for example. Now it makes me wonder about the first one. That one doesn't seem right anymore. Because 1 divides n. Maybe this is only true if it's not 0. Okay. I'm not sure I copied that down. Okay. So anyway, there's some multiplicative structure to R2 of n. It has to do with the factorization. And it turns out that so this fluctuates quite a bit. So for example, when it's not too hard to show, there are infinitely many n, such that R2 of n is bigger than any power, well, I guess I didn't need that sentence with omega. It's omega of log n to any power you want to prescribe in advance. So if you want something with more than log n to 1,000,000 different representations, there are infinitely many such n. Just make them really, really composite. So this is a function that fluctuates wildly. It has a certain average, but the min and max is all over the place. In terms of sums of Foursquares, the formula is a little bit simpler. Here we always have it's bigger than 0. Every integer is a sum of 4 squares. So if we look at R4 of n, again, there's several ways to write this, but one way of writing it. Yeah.
Can
Yeah, sorry, I meant to. No, that's what I mean to say. For any, you pick a b ahead of time, and R2 of n is omega of log n to the b. And analytic number theorists would gleefully write down some more complicated things, somewhere between big powers of log and small powers of n, and whatever. Yeah, it's like, no, that's fine, don't bother. Okay, R4 of n. Well, first of all, let's look at the average behavior of R4 of n, because it's one of the few times in our lives we can go to work and talk about the volume of a four-dimensional ball. So as you all know, just like I knew before I looked it up, the volume of a four-dimensional ball of radius r is pi squared over 2 times r to the fourth. So this, again, this is the number of lattice points, but now in a four-dimensional ball. So a squared of radius root x again. And because somebody worked out the volume of that, this is asymptotic to pi squared over 2 times x squared. So on average, R4 of n is like a constant times n. And again, there is a multiplicative type formula for this exact quantity. It's almost a divisor sum. So it's almost just 8 times the sum of all the divisors of n. But you have to throw out some divisors. Throw out the ones that are divisible by 4. In other words, keep the ones that are not 0 mod 4. And again, this fluctuates wildly in size, even though the average is just like x. This is quite small a lot of the time. So for example, the number of some ways to write 2 to the k as a sum of 2 squares. Most divisors of 2 to the k are multiples of 4, so you throw them all out. So this is actually exactly equal to 24 for k greater than equal to 2. So there are infinitely many numbers for which R4 of n is pretty small. It's only 24. But it also gets pretty large a lot of the time. So R4 of n is actually, does get asymptotically bigger than the average, though not by much. You can put in another log n or something like that. So it's a little better behaved, but it still fluctuates quite a bit. Here the fluctuations are on the small end. Okay, I guess 2 more things that I have to say. One is just to say that we don't know anything. Well, I don't know. There's nothing simple one can say about sums of 3 squares in terms of an actual formula.
Well, didn't Thomas Nugent say something simple about the sum of 2 cubes, the Hardy?
Oh, yeah. Instead of 3 squares, it's 2 cubes. Yeah, so that's the Ramanujan's taxicab number, 1729. Yeah, so Google 1729, you'll figure it out. Bing 1729, and you'll figure it out. Okay. Right, but so instead of 2 cubes, you get 3 squares. I don't even know if I should write anything about this, except maybe we can just show off that we know the volume of a 3-dimensional ball, since that's where we live. So 4/3 pi times the radius cubed, so 4/3 pi times x to the 3/2. So it's like x to the half on average. Of course, some still have no representations. There's not a nice multiplicative formula for the individual value R3 of n. I guess the last thing I just want to say is one way that people have studied this representation counting problem, which is not, it's not my preferred way. It's not the kind of tool I like to use, but it gives really good answers, so I got to give it credit. And it's related to the classical theta function. And this, by now, if you feel like tuning out, you can, because this is just totally for fun. If we define the classical theta function to be the sum over all integers, n equals minus infinity to infinity, of e to the minus pi n squared x. So the squares come up because we're only sort of summing over the squares here. And this is defined whenever x is a positive number. This is nice and convergent. And the relationship to this representation problem is, suppose I wrote down the sum of, from m equals 0 to infinity, of r sub s of m. Well, let's just do it for 3. So R3 of m times e to the minus pi mx. Well, R3 of m just counts the number of ways of writing m as a sum of 3 squares. So this is going to be a sum over triples, ABC, of e to the minus pi times a squared plus b squared plus c squared. Oh, sorry, a squared plus b squared plus c squared equals m. E to the minus pi a squared plus b squared plus c squared times x. And again, the m now disappears. We no longer care about what m is. We can just cover them all. So this goes away and this goes away. And this infinite sum factors as the cube of this infinite sum. Again, this is practice in doing like the binomial expansion on infinite things. But this is actually exactly equal to theta of x cubed. And in general, the sth power of theta of x exactly encodes the number of ways to write n as the sum of s squares. You could do similar things with cubes or any other power if you felt like it. And this function here, like so far, this is just like an algebraic clothesline. It just has the numbers hung on it, but it actually has nice analytic properties as well. And I'll just finish by writing down one of those, is that it actually has a very non-trivial functional equation. And you can use any program you want and draw the graph of this function. This is not the kind of equation that you would guess. But if you evaluate theta at 1 over x, it's actually tied to the value of theta at x itself. In fact, it's the square root of x times theta of x. This is quite a non-trivial fact. The functional equation for the theta function. This, I guess, basically comes out of Poisson summation. So there's some Fourier analysis going on here. And I won't even write it down, but I'll just say that this functional equation is actually instrumental in proving the famous functional equation for the Riemann zeta function. So if anybody has ever heard about the zeta function, it has a nice symmetry that's quite, it wouldn't be apparent. And the proof of that symmetry bootstraps this particular symmetry here. So this, we saw when we were looking at the number of representations as a sum of s squares, especially these average values, we saw that secretly these are counting lattice points in balls, in a disk, in a 3 or 4 dimensional ball. And the question that Yuri and I first started talking about was trying to count such lattice points in other shapes, so like an annulus or a segment of an annulus or something like that. So that's something that I am happy to talk about, but that's probably going to, I think, wait until people can disperse to wherever they want to be. But again, I'll be around all afternoon. So are there any questions?
Thank you.
Thanks.
So can you give us maybe one nibble from the item 4 that you didn't get to?
Yeah, and again, I will let you feed to your heart's content. I guess, so for example, if we're looking in a, well, it's hard to, I don't know exactly what nibble to give. So one of the things that in this paper that we're interested in is we want to count lattice points in an annulus like this, quite a thin annulus. And already it's verging on being a delicate problem because the annulus can be really thin. But we're interested in lattice points with a even more special property. If this radius here is capital N, then we're looking for lattice points AB such that n minus a squared minus b squared can itself be written as a sum of 2 squares. This is connected to writing n as a sum of 4 squares, which is a 4-dimensional problem, and this is like projecting it onto a 2-dimensional annulus, basically. And so the nibble, for people who have read or wrote the paper, is that I think that this number is omega of n over square root of log n. Sorry, theta of n over square root of log n. So if n is p to the L, I'd like to argue that it's actually p to the L over square root of L, as opposed to p to the L over L.
How thick is this annulus?
The annulus can be actually quite thin. The radius, you think of the radius as being 1 or something like that. I mean, really quite thin. But that it seems like that would be a really dumb thing to do, but that's the difference between, sorry, should this be root n as the radius should be root n? Yeah. Right. Because the point is, if we take 1 less than root n, this is about the square root of something like n minus 2 root n or something. So the numbers that we're representing are between n and, say, n minus the square root of n or something.
Then the area of the annulus is only root n.
Fair enough. Thank you. Same mistake. Yeah, thank you very much. The point here is that I want to argue in the nibbling session that the power of log on the bottom should be log to the 1/2 rather than log to the 1.
Our correct conjecture should be a little bit corrected.
That's my belief, but we'll see what survives. So that's the nibble.
Related to this Gauss problem, I'm counting the lattice points in the whole case, and the error can be there.
Yeah, it's a little bit different. And it's true that if you have a really thin annulus, then the error term becomes quite prevalent here. So the problem that they mentioned here is we sort of said out loud, if you have a big region, then the number of lattice points should be about the area. But there's an error there, and investigating how large that error can be is actually an interesting area of research. If you're allowed to draw the boundary, even for a convex region, but you're allowed to draw the boundary however you want, then the area can basically be the whole perimeter. You can just wind the perimeter to the left or right of every lattice point as you go along. But for a nice shape like a circle, then the area actually is somewhat smaller. It's going to be a smaller power of the radius than radius to the half, and exactly what the right power is still an open problem. Between a quarter and a third or something like that.
So we'll proceed in 112, 2209.
Very special case.
Thank you. Thanks for coming.